So let's go ahead and start this conversation with first taking a look at what timers are. Conceptually, timers are just like a timer you have in the kitchen. You set the, instead of sitting there and watching the time to make sure 20 minutes has passed, you set a timer which allows you to go off and do other things and then come back and when the time is up. So this way, you don't have to sit there and constantly watch the timer and make sure the timer is the time is correct. And if you're like me, if you're watching the time, you're watching it for the first 5 minutes, and then you get distracted, and 2 hours later you figure out, oh, the time has passed. The timer allows to kind of brings you back. In the computer system, so in real life, the timers are always ticking on seconds. You cannot make your individual tick of the clock longer or shorter. Each tick is a second, and then you count how many seconds or how many minutes you want and all of that kind of stuff. The interesting thing is in the computer timer system, the timer, you can actually decide two things. In the first, so you can decide how long each tick is from one to the next. So this we'll call it tick for now. How long does it take for the thing to go kind of equivalent to 1 second? But it's not 1 second. We can actually adjust it. So we can set the duration of tick to whatever we want. Okay. So that's that. And then the other thing we need to figure out is how many ticks we need. So number of ticks before we need to be called in. Okay. And so those are the two things you got to figure out. So for example, if somebody says wait for 10 seconds, you got to figure out, okay, how long should each tick be, and how many of those do I need to get to 10 seconds? Okay. So if you, for example, set each duration to, let's say, 256 microsecond, that means you have to take, if the duration is this, then the number of tick is going to be 10 seconds divided by 256 times 10 to the minus 6. So whatever that number is the number of ticks you got to do. Okay. And the nice thing about the timers, we have 4 separate timers. They work independent of each other. So you can have 4 different timing at the same time. And the nice thing is that I can go in there and say, okay, set my tick to this level and let me know when this time is expired, when so many ticks have happened. Now, the nice thing is that this allows us to cause an interrupt. So then I could be off working on some other, my processor could be working on something totally different, and at some point I can, it interrupts me, say, hey, your timer is up, it's been this long, it's now your time to come and deal with it. So that's kind of how these things work. Now the question is, so as I said, in this processor we have 4 separate timer subsystems. So we have 4 timers, okay, and they are named timer creatively timers 0 through 3. So I love the way engineers and computer scientists name things. It's very common sense, unlike biology, people who make up Greek names for the Latin names for things that you can hard time remembering. So this is the 4 timers. Each one of the timers will have a timer control. So for example, timer control 0 will have a timer control 0, and then they will have this other 2 register. One is called timer high and one is called timer low. Okay, for 0 it would be 0, for 1 would be 1, and on and on. Now, so this is used to configure. That's the job of this, as the name implies, is control or configure the timer, what we're doing with it, all of the various things. We're going to go through detail. Each one has a little bit of a different setting. And these basically configure a 16-bit quantity. Now, sometime our timers can only count by 8, sometimes they can count by 16. So if they count by 16, the bets in here, of course, there are 16 bets in here. They go from, and it counts from low of 0 to the high of F, 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 F for the 16-bit case. And for the 8-bit case counts to FF. So why is that important? Why do you care? So the way it works is you set a value in this thing, and when you set the timer, every tick, it increments the value in here by 1. So let's say you set this thing to FE. The next tick of the clock, this becomes FF. If it's 8-bit, the next tick of the clock, this goes to 0. Okay. At this point, it causes a timer 0 interrupt. If you have the timer 0 interrupt enabled. Okay. So that's how you know your timer is up and you need to go do something. Any questions so far before we go off and get into more detail? Does conceptually everything make sense? So when the only time you know your timer is done is when the timer low and high roll over to the maximum and go from a maximum back to 0. At that point, you get an interrupt. Any questions?
So what if you, what if they, like, for example, they give you the timer low and the timer high? How'd you figure out I guess, the steps in between before the interrupts?
Okay, so let's go take a look at that. Let's by the way, all the timers are identical to each other. So once we learn one, the rest are pretty close. They're not, I mean, I should say identical. They're very similar to each other. So once we know one, we can figure out the rest of them. Great question, Daniel. Give me just a minute and we're going to go actually look at one case. So everything, we put it in practice in a minute. Any other question conceptually before we get into the detailed practical side of this thing? All right. So let's take a look at that. Let's go to one of the examples that is in the book, and then we'll come back to it. So let's take a timer 0 and kind of walk through timer 0. Timer 0, you can set it to either an 8-bit or a 16-bit. If you set it to an 8-bit, it counts from 0 to FF. When it rolls over the FF, you're gonna get a interrupt. If you set it to 16-bit, once it rolls up to FFF and rolls from there to 0, you get an interrupt. So you can choose if you want, you need a lot of count or you don't need a lot of count. Okay.
So is that really all that's the difference is basically 16-bit is twice as many ticks as the 8?
Is it twice as many, or is it one is?
Or I guess maybe not twice as many, but is it the fact that you need more ticks before a reset, basically is what I mean? Because I guess it'd be like 64 times or something like that, right? Or
it would be one is 2 to the power of 16, the other one is 2 to the power of 8. So what is about 256? The maximum possible ticks you can create is 256.
Versus
The
like
maximum
8,000.
number is 32,000 or something like that.
Oh, so quite a bit more.
Yeah, it's 2 to the power of 16. Good question. 2 to the power of 16 versus 2 to the power of 8. The reason you choose 8 is, of course, easier to deal with, right? You only write 1 byte. You don't have to worry about the second byte and all that. So, but sometimes you want a lot of precision, or you want to count for a long time. You're forced into having to have a 16-bit.
Gotcha.
So yeah, if you can get away with it, we like to get away with 8. It's a lot easier to deal with.
But I guess if you're working in microseconds, 32,000 would come up pretty quick too.
Especially if you're if you're trying to wait for a second or 2 seconds or whatever.
Yeah.
So those are the issues we're going to run into in short order here. All right. So let's go through this. So this is the control. So timer 0 control. Timer 0 control controls the timer 0. T0 control timer 0. So first bit you set by turning the timer on or off. You can turn it on or off by setting 1 or 0 in here. You enable and disable it. You can decide whether you have an 8-bit or a 16-bit by setting that bit 7. Here you can set it, and we don't use a lot of these. For our purposes, let's go ahead and say we are using the internal instruction clock. And if you remember the internal instruction clock, we can set it by OSCON, but the default is 32 microseconds, right? That's the default one that runs. So, or you can have it tied to your external pin, and every time that external pin transitions, you get it counts as a tick. That's another way of doing it. So the nice thing for that is you can start counting events. So you could have that count connected to something, and the timer is used not to keep track of time, but to keep track of how many times that thing went up and down. Maybe you're counting fish or counting cars or counting whatever. Could do that. This one basically says, okay, do you want me to count when, if that only bit 4 is only matter if you're using bit 5 is set to 1, where you're counting the T0 clock transition, because it's saying, do you want me to count a low to high rising edge, or do you want me to count a falling edge? You can count either. PSA, so this is an interesting concept. Remember I said that the duration of the ticks can be adjusted. It's not fixed. Like in a regular timer, your kitchen timer, or whatever timer you use on your watch, if the unit is second or hundredths of a second and you cannot change it. Here, you can actually decide how long that is by setting these pre-scalar, post-scalar numbers in here. Okay, so these are something to remember. And this is the circuitry that makes the timer work. I'm not going to go through this right now. In the videos, we do spend a little bit of time going to lecture videos to go through it. But for now, this is good to know. So now the question is, how do I figure out the number of ticks? So the duration of ticks, I'm sorry, the duration of ticks. So the duration of ticks, for example, for this, how long for each tick would be basically the pre-scalar. The rule is sometimes there are pre-scalars, sometimes there are post-scalars. So all you're doing, you're taking the oscillator, whatever the oscillator period is, you are multiplying it by 4, you're multiplying it by the pre-scalar, and you're multiplying it by a post-scalar. Some of the timers have P-scale and post-scalar on them. Now, if they don't have pre-scale or post-scale, just put a 1 in there. This is how you figure out how long a tick duration is. And this is good for you to remember. So tick durations are basically the period of a clock times 4 times the pre-scale. All right, so let's go ahead and take a look at an example here, and we'll walk through it. It says, in a PICmicro timer 0, so let's go ahead and see what it's asking for us. It's saying, set it to 8-bit, set the pre-scale to 1 to 56, use the internal RC clock. So each one of these means something. This one says, okay, this is the clock, which means if it's internal RC clock, means I'm using the default clock. So this one basically says that TOS is 32 microsecond. Okay, so basically if I apply that to this one, it says, okay, I don't have a post scalar for this, so it's a 1. Pre-scalar set it to 256. This one set it to 32 microsecond. So my duration would be, and I'm going to do a little quick calculation on the side. It would be, actually, it's probably done for me. It's done.
It should give you it. It says like
It's done.
32,000.
It's done for me. It should be 32,760. What? I'm sorry. Go ahead.
Yeah, it says that, right? I was
Yeah.
about to mention that part.
Yeah. Thank you. It's one less thing for me to appreciate the help. So yeah. So you multiply. This is how long each tick will take. And then what they want us to do? They want us to
Number of counts for 1 second.
1 second. So now I found out the duration of the tick. So this is the duration. I got to figure out how many I need. So I need to wait for 1 million microsecond, 1 second, divided by that. So I have to wait for 30.5. The closest one is 31. So we rounded up to 31.
So for the time count, that's just saying that 32 microseconds is the oscillator, right?
Yeah,
32 microseconds.
yeah. Time per count. There's another way of saying it. Each tick of the clock,
Mhm.
each tick of the clock takes 32,000 microseconds.
Will it be before
it's just-
the next interrupt?
No, that's just single tick. That's
Okay.
just a single tick.
Okay.
It's
I
like,
just wanted to mention that line looks kind of confusing. It looks like you're taking 32 and dividing it by.
Oh,
and also
oh,
trying
yeah.
some of that.
you.
And
Thank
same
you.
with the cycle. So it just,
Oh,
that
thank-
one kind of confused me when I was doing
Oh,
the
I
test.
see, I
so-
see. What it's trying to say is 32 microsecond per cycle.
Okay.
Really done. 4 cycle per instruction times 256.
Okay.
Yeah, I see. Oh, I see what your point. Your point is, yeah. Sorry. This
Yeah,
is-
it
this
looks
is
like we're
describing the
dividing and,
units.
yeah, okay. That makes sense.
And then the number of ticks or number of counts, so this would be number of ticks or number of counts is 31 count, okay, to get to 1 second. So what does that mean? So that means interrupt happens when interrupt, so we are in 8-bit, which means we ignore the high, right? The high doesn't matter anymore. So we only care about the low, and the low, we want the low to count for 31 count. So all we do, we take the FF, which is 256, and we subtract 31 from it. And that gives us 225, right? Right here.
So
what-
the
so what-
256 comes from the fact that it's 8-bit, right?
Yep,
Okay,
Yep.
so if it was a 16-bit, you would do the,
whatever
2 to
the
the 16.
equivalent of this X number is.
okay,
Because 256 is, this falls into 0x100, right?
mhm,
So 256 is this number.
okay.
So now what I'm gonna do, I'm gonna take 255 and I'm gonna put it in timer 0 low, right? So what does that mean? That means 32,000 microsecond later, this amount of time later, this is gonna be 226. And then 31 times later, this will be 30 times later, it would be 255. When it rolls to 256, I get an interrupt. Which means it has been 1 second later and I'm getting an interrupt. Let me stop here. That's a big, big jump I made. So does that make sense to everybody?
Yes.
Yeah.
All right, so let's go back and take one thing I skipped is how did we come up with what to put in T0 con? And what we did, we took the definitions from here and decided what to put in there. So let's go back and take a quick gander at it. So we go, what did I do? I think I jumped quite far back. Okay. So we said, oh, I want to enable, let me erase everything. When we were trying to figure this out, we said, okay, we want this to be enabled. To enable it, I gotta put a 1 in it. We want this thing to be 8-bit, so we gotta put a 1 in here. We really want to use the internal clock, so we want this to be a 0. And we don't really care. You can put a 1 or a 0. It really doesn't matter because you're not using the T0 clock, so you can tell him whatever he wants to do. PSA, we do want to use a prescaler because if you don't use it, you get a 1 in there. So the prescaler, you want to set it to 0 so you can use it. And then they wanted you to use 256, so this is what you use. And of course, as I said before, this one is going to be don't care. Yes, Vlad.
Okay, so in order, I've been looking up at the lab. Couldn't we move a literal value into T0 con and just set the timers that way instead of saying like bit set F or bit clear F?
Yes.
Okay,
So what you could do, I mean, to do this, you would, that's the only way to do it, other than if you're setting it to 0, it's really easy to do. Or if you're setting it to FF, it's easy, but if you want a specific value, yeah, you gotta say move LW, whatever number you want. In our case, we wanted 225. And then we say move WF timers. I forget how they say timer 0. That's how it works.
okay, all right.
The reason clear sometimes is used because if you just gonna set it to 0, yes, you can put a 0 in here and move it in here, but it's a heck of a lot easier just to do this. Any questions about how timer 0 works or any of that stuff?
Is it relatively similar to like, let's say timer 1, 2, and 3?
Well, let's take a quick look at them, okay? Yeah, that's a great question. Let's take a quick look at it and then we won't spend a lot of time on it. Just take a quick look at it. And I'll point out some of the funny business they do in here too. So this is timer 1. I don't know why they did this. I would love to get the designer for this and sit down and talk with them. I'm sure they have a really interesting story to tell. But I don't know why on 0, how you turn the timer on was on bit 8 here in bit 0. That's what they did. The other one is, this is a tricky business. You want to pay attention. This one always runs on 16-bit. You just can control whether you do the read and write simultaneously from there in 16-bit or you do it in 8-bit. So it always is running 16-bit. It's just how you read from it. They have a different way of doing it. There are some other, the names a little bit changed. For example, system clock is derived from another source we usually use from our oscillator. And then prescale, it's got a little bit of a different choice for your prescale. There you had a little bit more flexibility, as you saw. This one you just have a little less. Timer 0 oscillator, timer 1 oscillator is enabled or shut off. There is some internal stuff that you can use in here. We don't use it. You can sync up. You want to sync up the external clock with the internal clock. If you're using an external clock, it has a phase lock loop inside, which is able to make sure the edges of those two clocks are synced up, if that's what you need. So it's got some additional features that are very unique to this processor. We typically, for this class, we're not using it because our goal is to learn about features that are very common across a broad range of processors rather than focusing on one. But if somebody wants to know that, let me know. And then the source for us, we always use the internal clock. Now, one thing to not get confused later on is it takes the oscillator, says when you take in the last example, when we took the period for the oscillator and multiplied by 4, this is the same thing, frequency divided by 4. If you take a frequency of a clock divided by 4 is the same as the period multiplied by 4, right? Because the relationship between frequency and that is 1/t. So sometimes they represent stuff with frequency divided by 4. Sometimes they talk about the time, the period. Most of the time we are interested in the period. So we usually write it in period form. Then we are calculating the duration of the clock. Let me stop right here. Are there any questions so far? So that was timer 1. And if you go to timer 2, it's a little bit different. The naming is a little bit different, but it's pretty much the same. One unique thing about timer 2 is that it has a prescale and a post-scale. Okay, so you have 2 numbers, so it gives you a little more flexibility if you want to use those 2 numbers. Okay, and this one is a little bit different in that it allows you to set the interrupt level at someplace other than FF rolling over to 0. Okay, so this one allows you to pick a different point for interrupts to happen. And then timer Z3, I don't know if there's anything unique about timer 3. It's just more or less a variation on the theme. Okay. Now, any questions? So once you learn timer 0, timer 1, 2, and 3 are variation on the theme. The names are a little bit different. They have a little more features, a little less features, but the process is the same. The process is you gotta figure out what the duration of tick is. Then you gotta figure out how many of the ticks you need before an interrupt happens. Okay, so let's jump right into the lab. Try to see if we can take some of these concepts and see how it's implemented in an actual code, because one of the things we haven't talked about is how do you set the interrupts, right? For each one of the timer, there is going to be a timer 0 interrupt enable, timers interrupt flag, timer interrupt priority, high or low, and then those things are available to you. So let's go ahead and jump in. I copied the code from the lab here, so we have it. So let's take a quick look at the code. And please jump in if you have questions. So the code is, this piece is just more or less the same. This code is rather written to do a very simple thing. It basically uses timer 0. And the duration is 1 millisecond. Every 1 millisecond it causes an interrupt that does something. Okay, so let's see if that is what it's doing. So this piece is, we've been using this set of code over and over again. It tells us what the processor is, what the default base is, and some flags that we need to set. Then we include this .h.include file where it's got all the constants and all the ports and all the registers defined. And here I defined a couple of local variables that I want to use: state least significant and list state most significant. We'll find out what they are. And then, as you can see here, we have main is where our main code is running. And we're only using high priority, it looks like, because low priority is not defined. And then here's our main code. So main code comes in and does some standard things, make sure all the variables are clear, make sure all your ports are clear, make sure all the ports are set to digital. And then it does some other things and you can change them, but in this case, set certain pins on Trish A. It looks to me like it puts everything as an input except the least significant bit of port A. So RA0 is the only one that's an output based on what is set here. Oh, and then one other thing it does, we haven't seen, this is a bit of a new, it goes and changes this register OSCON so that our frequency T oscillator, this is basically saying that T the period for our oscillator is 0.25 microsecond, right? Because it gives us a frequency of 4 megahertz. 1/4 times 10 to the 6 is 0.25 microsecond. Any questions? All right. So and then here is some familiar things. If you want to get an interrupt, you have to interrupt all the peripheral interrupts, and we typically do a global interrupt enable as the last thing after we've got everything set up, just to be safe, so an interrupt doesn't happen in the middle of us setting the interrupts up. You usually leave the global interrupt enable as the last thing, get everything else set up. So it looked like we are setting an timer 0 interrupt enable. We are enabling it. We are setting the priority to high by setting it to 1. We are enabling the peripheral, we are setting the enable priority level. Okay, we're saying, okay, interrupts can have priority level. That's great. And then we are saying interrupt clearing the interrupt flag. So we say, oh, nobody has interrupted so far. We're good to go. And then, okay, here comes very interesting. I would like you guys to take a minute and work with me. It's putting T0 con to 41. So let's go ahead and go over here. So the T0 control is set to 41, which is 0, 1, 0, 0, 0, 0, 0, 1. So we want to know what it is. So this one tells me, as far as I can tell, this one is telling me that the thing is disabled, right? If you go back, let's go back and take a look at it real quick. Okay, so this was set to 0, so it's disabled, and this is set to 1, which means what? Oh, we are running it in 8-bit. Okay, great. So that makes our life a little easier. It's 8-bit. And then this one was set to, these two are set to 0, which means use the internal clock. So we're running 4 megahertz, and I don't care about the other one. Okay, so let's go back here. So this says the timer is disabled. This says we are running at 8-bit. This is saying we are using internal clock. We're not using an external thing coming in. So our TOS is 1/4 of microsecond, as we said. And this one is saying something. Oh, this one is saying rising edge or falling edge. We don't care. We don't care. And this is saying use the PSA, use the scalar, and this is telling what scalar we need to use. So let's go back and take a look at what scalar we're using. So these bits were 0, 0, 1, and then we go down here and look to see what 0, 0, 1. 0, 0, 1 means the scalar value is 4. You see that? 4.
Well, the PSA is a 0, so it's a, so what does that indicate?
Says you're going to use a pre-scalar. If you set the PSA to 1, it says you're not using it.
Okay.
It's kind of some of the ones and zeros could have done better, right? I would think a 1 would say use the PSA, don't you think?
Yeah.
Yeah, but it is what it is. So you got to kind of go with whatever this.
Manufacturers.
Yeah, whatever.
I guess what they strive on is the names, not so much the settings.
Yeah. So this one is a pre-scale is set by 4. So let's find out. So remember what the rule is. The duration of tick, the duration is how long it takes for a single tick is now going to be 4 times the TOS, which is 1/4 of a microsecond, right?
Mhm.
Times pre-scalar, which is 4. Since I don't have a post-scalar, is 1. So this will be basically 4 microseconds. So each one of my ticks only takes 4 microseconds. Make sense?
Yep.
So that's great. So we got this one. Let's see what the rest of the code is telling us. So is it lying here? No, okay. It says timer 0 tick is 4 microseconds. We agree. We are in agreement. Okay. Then it says clear this thing, clear timer 0. That's what the question Vlad has, is that what if I don't want to put a 0 in here? Yeah, this is we could make it more precise, but I think this was kind of a little rough. So this is basically saying I'm going to set the timer 0 low to 0. So let's go take a look at what happens. So if I set the timer 0, so if I set timer 0 low to 250, what did I say? To 0. That means it has to count all the way to FF, right? And when it flips back here, then an interrupt will happen. So how many ticks? Number of ticks is going to be what? It's going to be this minus that. So number of ticks are
256.
256. Now let's go read the code one more time. So the bottom line. So how long does it? So time to interrupt. How long does it take before an interrupt happens? You're gonna say, well, each tick takes 4 microseconds. I got 256 of these ticks. So that's how many it takes. So you multiply all that and you end up with 1,024 microsecond, right? Or another way to put it is 1.024 millisecond. Fair enough. Let's go read the code. Let's go read the code and see what it says. So anyway, the last thing it doesn't tell us. And he says, oh, is this lying? It says 256 count or 1 millisecond to timer 0 interrupt. Well, it looked like he's 24 microsecond off, right? Does everybody agree with that?
Yeah.
How do I fix it?
Well, you can take 1 tick away, right? Or a couple or 6 ticks away.
Yeah, and how do I do that? Basically what I'll do, I'll come over here and I say move LW 6. So I put a 6 in there. And then instead of doing this, I'll go then now I'm precise. You see that? Now precisely one, well, precise is questionable, but I'm not as far off as this. At least theoretically, I'm not starting at this, I'm starting at 6, right? And I'm counting all the way to F. So that means my number of tick is 256 minus 6 is 250. So if I do 250, then that becomes 250 and this becomes 0. I can look closer. But for these kind of timing, a few microseconds this way and that way, the tolerance is within a percent or so, we'll call it good. Any questions? Okay. So now we got so what has happened? We've set this up so this thing is going to interrupt us 1 millisecond every millisecond, right? So main loop does nothing. You can be doing the stuff in the main loop because once the timer is set up, you're free to execute your code. I don't know, you're harvesting Bitcoin or some cryptocurrency while this thing is waiting for the next event to happen, time for lunch or whatever. Although I don't recommend using this processor for Bitcoin mining, you will not get anything out of the deal. Okay, so you come out here and say, okay, I remember that timer 0 was set to high priority. So after 1 millisecond, this is going to get called. I'm going to check to make sure that is interrupt 0 who's causing me an interrupt. And if it is, I'm going to branch to interrupt 0. Otherwise, I'm going to return. I don't want to do anything. I return from interrupt, which is by branching all the way down here. I just clear the flag and return. That's all I do. In timer 0, all I'm doing is basically going in there, incrementing state, this least significant memory location. And then,
hey, quick, Azad, why would we need to check to see that it's timer 0? That's the interrupt. Like if there's nothing in the code that would suggest another interrupt.
perfect. You don't have to do it, but it's a good practice because guess what? This is a baseline code that you're going to use and add other things to it, right? So
Gotcha.
if you don't put little error traps for yourself in there, you could do something with forgetting to come and catch it. Does that make any sense? So maybe I add another interrupt to this thing. This is
That's
the
totally
safe part. But you're absolutely right. As this code stands, I don't have to check.
Fair. All right, just checking.
Good check. Good check. Okay, so what I'm doing here is this. I'm just incrementing a 16-bit counter. Basically, all it's doing is saying, okay, everything through this thing increments it. So think about the state variables I have in here that I've declared in here. Just think about them as Just think about them as two 16-bit quantity. Usually one of the variable I called state, least significant byte. Another one I called state, most significant byte. And this
Those are
one
both
is
16. They're 16 each.
8-bit each, right?
8 each, okay.
8-bit each. So this goes 0 to 7. This goes 0 to 7. They're separate bytes in the memory, and they are all treated as separate byte. But I really want to treat them as a 16-bit. So what I do is I increment this one. Okay. Once this rolls over to 0 again, I'll increment this by 1. And that's what I'm doing. So let's go back at the code and look at the code real quick. So if you look at the code, you'll see it comes in every time, every millisecond through the loop, it's going to increment this by 1. You see that? And when state least significant byte becomes 0 again, that means it rolled over. Now I got to increment the most significant byte by 1, carry. So I'll do that, increment it, and then I'll return. Okay. It looks like every 250 millisecond or every quarter of a second, I toggle RA0 by 1 and toggle them, turn them on, turn them off. So every quarter seconds turns on and turns off. So this gives you an idea of how timers work. Okay. But what I wanted to do in here, also introduce another concept, which you need for this lab. If you go to the lab and take a look at what the lab wants you to do, your lab wants you to basically deliver different levels of power through RA0 at 215 hertz. Okay, and the way you deliver different levels of power in the computer's world, the digital world, we change the duty cycle. So what is a duty cycle? Duty cycle is on time over period. So for example, if let's say, so they want me to do a 250, see what they're doing? They're saying you got to run this thing at 250 hertz, which means the period is 4 milliseconds. So what do I do? So I say, okay, the period is 4 millisecond, okay? Because of this, 1 over 250 is 4 millisecond. And then I say, okay, that's great. Now what do I do? So they said every so often come and change the power from 100%. So when it's 100%, at 100%, the on time for this thing is 4 milliseconds. It's on all the time. For 75% is 3 millisecond, right? For 50% is 2 millisecond. You see the 2 over 4 is 50%. And then if I want 25% is 1 millisecond on, 4 millisecond period. That's that. And if I want 0 power, never turn it on. Does that make sense?
So you like decrementing the time?
Well, you got to hang with me. It's a little more complex than decrementing time. All I'm trying to kind of right now explain is what is this, how do you get a percent of maximum power? Then the way you adjust it is by making the on time longer or shorter. Are we good so far?
So real quick, just to make sure, because I can only see the 175. So is it, so basically
Let
goes,
me, the problem is that I use the annotation, so now I gotta come and I move it, everything moves and messes it up. So let me go, okay, go ahead.
so is it, so basically 100% is going to be on all the time. So be 4 milliseconds, and then 3, 2, 1, and then obviously 0.
Yep.
Okay.
And
That's what I
then,
just
and
wanted
then
to make
back
sure the
up.
timing.
So you've got basically, you can think about this as having 10 unique cases. You see that?
Mhm.
10
So the
unique.
10th case will just basically be branched back, right?
So 9
Okay.
cases, you're absolutely right. So there's 9 cases you have to deal with. So what you do in your interrupt, you could basically says, okay, I know my count, my state variable, right? Remember the state variable we created? So you can say my state variable is 16-bit, right? And I know this counts every 256 millisecond, right? So every time the state most significant bit. So every count, if this goes from 0 to 1, I know it's been a quarter of a second, right? Everybody okay with that?
Yep.
Other folks, is okay? Anybody has question? Why is it a quarter second? Because this had to go from 0 to 255. Each interrupt caused one increment and all that. Great, thank you for feedback. Okay. So what we're going to do is we're going to say every count of this is 1. So that means that all I have to do is to go from here to here every 2 counts. So I can say, okay, when I have to do this, when most significant byte is 0 or 1, that gives me 2, right? This one you can say when most significant byte is 2 or 3, right? Because he wants you to turn it on for half a second each case. So that's how you know which one are you in. And then when you get over here, you can clear the state variables. So you start the process all over again. And this is a very common way people do these kind of work, because you only use one timer, but you keep a count of how many interrupts have happened, and that's how you decide which state you are in.
So are you testing the most significant bits then?
Most significant byte, the state,
Or byte.
this whole variable. I'm looking at this thing. If this is 0 or 1, then is the first half a second. If it's 2 or 3, then is the second half a second. If it's 4 and 5, then is the third one. So I know which one of these I gotta do.
Okay.
Okay. And
And so you're not testing each individual bit, right? You would test the byte for value.
Yes, and there are, yes, absolutely. There's a equal skip function opcode that it's very useful for you to use. So let's go to the code and see kind of how we do that in the code. Let's just go back to the code and take a look at that. So if I wanted to implement this thing, let me clean this up. If I wanted to implement this, see, this piece of code I would leave alone. Okay. So this piece of code I would leave alone, and so you do that branch. So here is where I start my code in here. Okay, so I'll say, actually, let's leave that alone too. So I increment this thing, I'll test this on, and then if it's not 0, I don't want to increment this down, so I'll wait here. Don't do branch to, I don't know, power. And we're gonna have so we're gonna, what would it be, starting at 100, I think, right? We're starting at 100. So we're gonna do power 100. We're gonna jump to power 100. I'm gonna name it, but you can name it whatever you want. Actually, let's do this. Sorry for keep changing my name. Let's call it state 1 to match the lab. Lab had 1, 2, 3, 4, 5. So I'm gonna go over here and I'm gonna be here, right? And I'm gonna say, okay, I want to do this. What would be the easiest way to do it? So I'll do this when there is a function called move, move LW two. I gotta think, equal greater than, okay, fine. That's fine. Skip. All right. And then I have this function called CPF skip greater than. Actually, I'm going to use less than, sorry. Less than. And what I'm checking is the state variable most significant byte. So I'm going to check to see if the most state variable is 0 or 1, which means if it's still on the first half a second time, which means what I have to do is I have to be 100%. If I want to be 100%, all I have to do is bit set f port a comma 1. Oh, 0.
So that's comparing. Oh, so it's comparing W to state MSB.
Yeah,
Okay.
I'm gonna clean it up just a little bit. My apologies for this. So let me do one more thing. So what I want to do, I don't want it to skip because it's easier to write a code where. Let's do this. What I'm trying to do is kind of structure it so I don't have to do a lot of jumping around. Okay, so I'll come here and I said if we are in the first, so. Okay, so. No, actually, I'm getting myself confused. So this one is a, can't do it on the fly unless then, okay.
So basically, if that's less than 2, then it would do, or then it'll.
If
skip
it's
the
less than
branch?
2, it will skip, right?
Okay.
If it's greater than 2, then we must be on the later times because each one of those states takes half a second, right? So we should be down the path.
Can I ask you a quick question since you
Sure.
had that up? How do you get that pop up right there?
Oh, I just,
Mine doesn't do
I'm
that.
just rolling over the bits and it pops up.
Oh, mine doesn't do that.
Oh,
Okay,
you might have had to compile it and debug it before it does.
Oh,
It should do that. This is actually wrong code anyway. This is the previous code is giving me the answers for. Okay. So then none of that kind of, I got it straight. So what we're doing, so we're basically trying to implement this. So we got to do this based on the problem, we got to do this for half a second. And the way I know is the first half a second is because the numbers are either the state, the most significant bit is either 0 or 1. And then because that's a quarter second for 0, quarter second for 1 is half a second. And then I do this and then do the next one. So let's go back here. So I'm basically comparing it to 2, saying if it's less than 2, then it's I need to take care of state 1. So I'll do whatever I need to do to take care of state 1, and then when I'm finished, I'm done. So when I'm finished with this thing, I'll just branch to just like this. Now, state 2, I know if it was this, I would have taken care of it. The only reason I'm here is because the number is either bigger than 2 or bigger. So I literally can copy, now that I got the pattern down, I can get this one, put it down here and say, okay, now I want to be in state 2. So this was 100%, right? Let me put that up here actually. So state 1 is want to be 100%. State 2 wants to be in 75%. So what do I do? Okay, I say, okay, let's do the same thing. Just this time, make sure it's less than 5. 0, 1, 2, 3, 4. 4. Less than 4. That means if it was 0 and 1, this guy would have taken care of it. Since I'm here, it must not be 0 and 1. If it's less than 4, it must be 2 or 3, which is the second one, which I need to have it at 75%. Now the interesting happens. How do I know where I am? And this is where you know your period is 4 milliseconds, right? And you're gonna your period is 4 milliseconds. Let me get it draw. Your period for your clock is 4 milliseconds, which means you get an interrupt. You get 4 separate interrupts, right? So if I'm on 75 milliseconds, all I have to do is make sure that for this period is 1, for this period is 0. So how do I know what is that? Well, I know the least significant bit, the state variable least significant bit, counts up 0, 0, 0, 1, 1, 0, 1, 1. So all I have to make sure is that do a test and say as long as it's not 1, 1, then clearly. So how do I know that? Well, there's many ways I could do that. One of the simplest, well, we've done this before, right? So what I could do when I get to state 2, I check myself and then branch to state 2 here, branch to state 3, because if it's not this, then we want to start the next step. Okay, so the question is, what do I do here? So here, I don't want to go 100% power. I want to really go 75% power, which means I want to be set to 1, except for one case where this is 1, 1. I could do something like this. I could say move, and we got to figure out how we're going to arrange that. We're going to move LW. We're going to put a 3 in here. And then we're going to end WF with state least significant byte, comma 0. We don't want to mess up the state variable, so we got to put it in the W register. And then we can say if it's branch not 0, go someplace else, do something else. Okay. So if we are here, so what happens is if I end the least significant bit with 1, 1. Okay, so if it's 1, 1 and it comes back as non-zero, then it must be one of these. Then must be one of these 4 cases, because if it's ended with this one, the answer comes back at 0. So what I'm going to do, I'm going to cheat a little bit and nobody's going to complain, because what I can do, instead of having the period on first and off later, for me, is a little easier if I do this for the period. So I'm going to say, look, I am going to set it to 1, except for that last case. So now we got to think about how we're going to do that. So as long as it's non-zero, so if I tested it and it's not 0, then I'll go to state 2 let's say on. I'm making up these names as I go. So we probably can come up with better names for it. So I go to state 2 on, which is another label. And if it's 0, then it means I didn't do the jump and came to the next one. So all I have to do it's bit clear F port A, comma 0, and then branch to done, because that's what I wanted to do. And if it was 0, sorry, branch not 0, this should be set. And then if branch is 0, then you come here, jump into this label, and then you make a label called state 2 on. And
Missing
here,
the E in that one.
what's that? Thank you. I don't have to execute it, so okay, but thanks for letting me.
Okay, I just didn't know.
No, that's great. Thanks for letting me know. I was just being a little silly. Now I'm gonna clear it. No, I'm sorry, I'll go back and explain it in a minute. So we want branch not 0. So if it's 0 comes in here, perfect. So that would be clear and that would be set. Let me stop right here. The rest is pretty much kind of modifying this, but I want to, since I went a little bit back and forth, I want to make sure we talk about it a little bit. So so you have 9 of these states created, okay? And you got to think through each one. You kind of say, okay, in state 1, I made sure I'm in the first 256 millisecond timers. And all I have to do is, this was really easy because in this, as long as you're in state 1, you just set the port to 1 and was on all the time, 100%, life is good. On the second state, life became a little more complicated because you needed to make sure that it was for one of the 4 milliseconds in a cycle, it was off, for the other 3 was on. And looking at it, I said, look, if you take a 3, a 1, 1, and ended with this, then for 3 cases, it would be a non-zero. For 1 case, it would be a 0. So what we did basically says, look, what we're going to do is take a look, ended with 3, and if it's 0, then we're going to clear the port A. If it's 1, then we're going to set it to 1, and then that's it. Okay, so let me stop right here. The red, hopefully, if you understand this, then you can replicate it 9 more times for the other cases. Okay, and some of you may even come up with better ways of doing it than that. And I would encourage you. This was just to give you an overview of how we would do it, as opposed to being exhaustive or the optimum way of doing it. Okay. This way of doing it, this is called kind of creating a state variable and using that state variable to figure out what's going on and scheduling different events using the same timer. We do that quite often in visual systems. All right, let me stop right here, see if there are any questions about what Lab4 needs. I'm sorry, Lab5. This is Lab5. Lab5 needs any question, anything you want to talk about at this point.
I guess I got a real quick question. So obviously I can understand the states and jumping from each one, but you said we have 9 cases here, so technically we'd need 18 bits to check, right? or
It would
20.
be, yeah, so, yeah, basically, since each one takes 2 counts, right? Because each count is only 256 milliseconds, a quarter of a second. So you wait for 2, yeah. The last one will be probably, what would be the last one? Would be 17 and 18, right?
And then if it's anything greater than 18, you would just branch.
Actually,
or
what I
reset.
would recommend, sorry for the interruption, but what I would recommend when you get to the state 9, you basically clear both state variable, least significant, most significant, and start over it.
Okay.
Because if you clear those variables, what happened? You start back at next time the interrupt happens, it comes in and the state variable is 0, so it starts from 1.
Oh, so there's really no reason to branch at that point. You would just
Right.
return and then you're automatically starting over.
Right, in your last state, whatever the state 9 is, you do all the cleanup. You clear the state variable least significant bit, you clear the state variable most significant bit, you do all of that stuff before you return.